Hello and welcome to another episode of Recently in the Support. Today I would like to talk about a topic which is quite important for EMC simulations. When we are simulating low-pass filters, for instance, we are often using ferrites. Ferrites are quite good to model in CST Studio Suite because we have the Debeye model, for instance. The Debeye model considers the drop in the permeability with a frequency. So we are giving a permeability, a static permeability at low frequencies, and when the frequency increases at a certain point, the permeability is dropping down to a value of 1. That's quite good, and that's very helpful for simulation. But what we are not considering there is the influence of an H field present. Imagine you have a ferrite and you have a current going through this ferrite at a working point, some differential mode current going through the ferrite. It might be a high current which is going through there, and the H field might influence the permeability locally in the ferrite. Well, that is typically not possible to simulate in a high frequency simulation because you don't have the nonlinear pH curve present. But CST Studio Suite offers a really good workflow where you can combine the low frequency simulation with a high frequency simulation. So in the low frequency simulation, you're simulating the influence of the H field on the static permeability, and then you're considering the static permeability locally in the high frequency simulation in order to take account this effect. Now we'll show you how to do that in CST Studio Suite. Let's start. Now here we go. This is our example model. It's 2 bus bars made of copper, housing made of PEC, and we have a ferrite material going around the copper bus bars. And this ferrite material we've been defining using a Debye first order model. So here we see we have a static permeability of 10,200, which stays quite constant up to 1 megahertz, and then it drops down to 1 at approximately 200 megahertz. We also defined some differential mode and common mode excitation here, and you see the impedance plot. Red is the differential mode impedance and green is the common mode impedance, where you can clearly see the frequency dependency there above 10 megahertz. Now we are defining this nonlinear ferrite material with a nonlinear pH curve. So we are defining a material, a normal material with a nonlinear pH curve. And you can see it here. I'm opening the mu over H. You see that the permeability is dependent on the H field. So this material we are now applying to the ferrite, and then we are using it in our workflow. The workflow we will reach from the schematic simulation project and its biased ferrite EM coupling. So first we define a magnetostatic simulation and we have a high frequency simulation. Both will be coupled together. And if we go to the magnetostatic simulation first, we will have to extend a bit the bus bars in order to be able to define some currents on it. There you can see it. We have a differential mode current defined on the both bus bars. One is going in, the other one is going out. And we have a current parameter defined so that we can do a parametric study, the influence of the current on the permeability. Of course, we have to also to apply the normal material for copper to the bus bars for the low frequency simulation, and then we can switching over to the high frequency simulation, where we will define the ferrite material not as a first order Debye model, but now as a generalized Debye model. And this generalized Debye model is exactly made for this purpose. The mu static is 2, but this one will be adapted automatically by the low frequency result of the permeability. So this value is only kind of variable. This will automatically be changed by the low frequency simulation. And the rest is the same. You see the Debye model with the dropping permeability for high frequencies. Now we have to say that we would like to use the pH curve as a field dependency, and the biasing field is detected automatically. That means a CST Studio will automatically find the right source for this mapping. Now we can define a 100 ampere job. I'm changing the current parameter to 100 ampere in the task parameter list. And then I'm going to duplicate this task and rename it to 10 ampere. And then we can do the same simulation with 10 ampere in order to find out what the influence on the impedance is. So I'm switching this to 10 ampere. And now we can start the simulation task. First, I will deactivate this pure HF simulation. And now we are running it. As soon as we have the results, we can compare the impedance plots. But first, I would like to show the permeability, the local permeability in the ferrite. You see, for 100 ampere, we have a strong influence. We have really some local effects here going on. And if we go to the 10 ampere calculation, we will see, well, almost no effect. Everything is red, but I'm changing a bit the scaling. If I'm putting that up to 8,000, no, maybe 9,000, then we see a small effect, but a really small effect on the permeability. So now we can compare the impedance plots. We see for the common mode impedance, the red curve is 100 ampere and green is 10 ampere. So you see that 10 ampere is very near to the purple curve, and the purple curve is without considering the nonlinear pH curve. So for 100 ampere, it's really important to use this workflow in order to be able to simulate with the effect of a nonlinear pH curve. I hope that helps you in your daily business. And if you have any questions, feel free to contact us. You will find our email address below. See you next time. Goodbye.